In this video, I will present another way to count objects. Usually, when we count objects in a certain problem, we use direct counting, where we count how many objects or arrangements satisfy the condition. On the other hand, in complementary counting, we count how many objects do not satisfy the condition and then subtract that from the total. Usually, direct counting may have so many cases, so it might be easier to count how many do not satisfy the condition. Our first problem, how many 3-digit integers do not have all digits the same? Let's do it in two ways, one in direct counting and one in complementary counting. In direct counting, we have to consider two cases, where all 3 digits are different, or when 2 digits are the same and the other one is different. Let's consider the case where all 3 digits are different. There's 9 choices for the hundredth digit, since it could be a number from 1 to 9. There's 9 choices for the 10th digit. It could be a digit from 0 to 9, but it couldn't be the one that we've chosen the hundredth digit. There's 8 choices for the 1st digit. You could choose it from 0 to 9, but you cannot let it be the number that you use in the 100th digit or the 10th digit. So 2 choices are out, so you have 10 minus 2 equals 8. Since when we choose them, they're independent, so we have 9 times 9 times 8 equals to 648 total ways. Now we consider case 2, where 2 digits are the same and the other one is different. When hundreds and tens are the same, there's 9 ways to choose them, since they could be a number from 1 to 9. Then, there are 9 ways to choose the ones such that it will be different from the other 2 digits. The case where the hundreds and ones are the same is similar. So we have 81 plus 81 is 162. We got the 81 from multiplying 9 and 9, since they're independent possibilities. Now we consider the case where the tens and ones are the same. We could choose them from a number from 0 to 9, but we have different choices when we choose a different number. When we choose a number from 1 to 9, we only have 8 choices for the hundreds, because one of the choice will be taken from the tens and ones, and we cannot repeat that. And we also cannot use 0. On the other hand, if we choose 0 for the tens and ones, we have 9 choices for the hundreds. Hence, we have 9 times 8 plus 9 equals to 81 total. For case 2, we have 162 plus 81 equals to 243 numbers. We have to sum up both cases. Case 1 gives 648 numbers, case 2 gives 243 numbers, so we have 891 numbers in all. This time, we will solve it by complementary counting. The total number of 3-digit numbers is 900, since you have 9 choices for the 100th digit and 10 choices for each of the tens and ones digits, and they're independent, so you have to multiply them. Now we see how many numbers do not satisfy the condition. There's only 9 of them, 111, 222, 333, all the way up to 999. We could only have control over the hundreds, then the other 2 digits have to be identical to it. So our answer is 900 minus 9 is 891. In here, 900 satisfy the condition. 900 are the total, 9 do not satisfy, so 891 satisfies. This is clearly much faster than direct counting. Next question. How many 3-digit numbers are not multiples of 7? The 3-digit numbers are from 100 to 999, so as we have seen, there's 900 3-digit numbers. How many multiples of 7? Now the smallest one is 105. It's 15 times 7. The next smallest one to add is 98. But it's not a 3-digit number. Now the largest is 994 equals to 142 times 7 because after 994 is 1001, which is not a 3-digit number. So we have from 15 times 7 up to 142 times 7. So there's 142 minus 15 plus 1 with the 1 for the last number is 128 multiples of 7. So our answer is 900 minus 128, 772. Again, there's 900 total, 128 do not satisfy, so 772 satisfies. This could also be applied in probability. Next question. If you flip a fair coin 5 times, what is the probability that at most 4 heads come up? The total number of possibilities is 2 to the 5th, because for each coin, it will either be heads or tails. And so there's 2 possibilities for each coin. So this 2 times 2 times 2 times 2 times 2 is 2 to the 5th equals to 32. Also, these possibilities are all equally likely. Now let's count the unwanted possibilities. The only unwanted possibility is when all 5 are tails. That's only one. So there's 31 possibilities that satisfy. 32 minus 30 minus 1 is 31. So our answer is 31 over 32. Next, how many 5-digit numbers have at least one zero? You could see that there are 90,000 5-digit numbers, since they range from 10,000 and 99999. Let's count how many there's without zero. We consider them each digit at a time. For the 10,000th digits, they could be from 1 to 9, same as the thousands, hundreds, tens, and ones. So there's 9 to the 5th, because there's 9 choices for each of them, so that's 59049. Let's see how many have at least one zero. There's 90,000 total, 59049 have no zero, so 90,000 minus 59049 equals to 3951 have at least one zero. Next, how many 4-letter words with at least one vowel can be constructed from the letters A, B, C, D, and E? The number of 4-letter words formed with the letters A, B, C, D, E is 5 to the 4th because there's 5 choices for each letter. We get 625. Let's see the number of 4-letter words without vowels. All of the 4 letters have to be consonants, so it's either B, C, or D. There's 3 choices, 4 letters, so 3 times 3 times 3 times 3, since they're independent, that gives 81. The number of 4-letter words with at least one vowel is 625 total minus 81 without any vowel equals to 544. Let's go to some challenging problems. These are difficult and complementary counting will be extremely helpful. Question. 2 tour guides are leading 6 tourists. The guides decide to split up. Each tourist must choose one of the guides, but with the stipulation that each guide must take at least one tourist. How many different groupings of guides and tourists are possible? Let's see, what's the restriction? The restriction is at least one tourist. If we remove that restriction, each tourist could go to any of the 2 tour guides. So there's 2 choices for each of the tourists, so there's 2 to the 6 choices total, that's 64. Our unwanted case are when one guide gets all 6 tourists. There's only 2 ways. The first guide gets all 6 tourists, or the second guide gets all 6 tourists. 2 ways. Hence, the valid groupings are 64 minus 2 is 62 groupings. Because there's 64 total, 2 of them which do not satisfy. In these kind of questions, we have to read the whole problem to see what's the restriction. So we could count how many do not have them, and how many are there total. Next, how many different ways can 6 friends stand in line if 2 of them, namely A and B, refuse to stand next to each other? Let's solve this one step by step. The first step is to find the total number of ways. We have known that the number of ways to arrange n objects in a line is n factorial, which is equals to n times n minus 1 times n minus 2 up to 1. So there's 6 factorials, there's 6 friends, so 6 factorial, 720 ways. Or in unwanted cases, the ones that you don't like is when A and B are together. So we have to count how many cases where both A and B are together. Here are the cases where A and B are together. We could see here that there are 10. 5 in which A is before B, and 5 where B is before A. These are all the possible positions, as you can see. In each of these cases, we have to still arrange the 4 of them in any order. Now, there are 4 factorial ways to arrange the other 4, so that's 24. But since there's 10 separate cases, there's 240 unwanted arrangements, which is 10 times 24. Since there's 10 places and 24 ways for each place. Hence, there are 720 minus 240 equals 480 valid arrangements. Summary. Complementary counting is counting how many do not satisfy the condition and then subtracting that from the total. It could also be done in probability and use complementary counting if direct counting would need too many cases.